Hello and assalamu alaikum. My name is Fakisha. In this video, we will be talking about AVR timer programming in assembly and C. So here we have first program of assembly, that is we have to make in the phone program we are creating a square wave of 50% duty cycle with equal portion high and low on the port B. 5-bit timer 0 is used to generate the time delay, analyze the program. So in this video we will be analyzing the program. So you can see we are using dot include over here, and then we are using dot macro in it stack. So we are setting a stack. So we are using LDI R20 higher remnant. So we are using LDI R20 as high, and giving it a loading data intermediate as R20, it is high, that's all one. Then we are using output SPH R20, and then using again LDI R20 is low, and then outputting SPL as low, that is R20. Then we are and macro we are using init stack. Then we are LDI, and we're loading data intermediate R16, that is fifth bit. That is we are using R16 and uploading the 20 on the for the fifth bit, that is 10000. So SBIDDRB port BB5 as an output, using BB5 as an output. Then we have using BB5 as an output. And we have LAR17 as 0. Then we are using output R port B R17 as clear bit for PB5, and then we are using our jump. Then there is a delay function, and this delay function is causing a delay, that is we are first loading the 20 with 0 cross F2. Then we are using a load timer 0, that is TCNT0, that is load time 0, timer 0. Then we are outputting TCCR0 R20, and this one is for timer 0 normal mode, int clock or no prescale. So then we have TIFR, that is TIFR is used for um, reading TIFR VR. Then if TOVO is set, then skip next instruction, and at the end we have output as timer, output as stop timer, this one. And then we have this out TFR R20 is clear TOVO flag by writing a 1 to TIFR. So we are closing it by writing a 1 to a TIFR. So if we move on to our next program. So our next program is it is actually R6, yes. So our next program is find the delay generated by timer 0 in the following code using both of the methods of figure 8. Do not include the overhead due to instruction XTAL 8 megahertz. So using 8 megahertz crystal over here. So we are using again macro and check for a and it is a similar code, same things. I think this code has been repeated, I think. Yes, and it would be yes, this code has been repeated. So we will move on towards next code which we were doing. Okay. So 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 in this program, in the for program, how long does it take for the PB3 to become one? Do not include the overhead due to instruction XTAL 8 megahertz. So we are using SBI DDR-B3, that is BP3 as an output, and CBI port B3, that is PB3 as equal to 0. Then we are using LDI R20, we are giving 89. Then we are using out OCRO R20, that is OCRO is equal to 89, and then LDI is equal to R20, LDI loading data R20 into 95, and then we are using clock TC and T0 is equal to 95, and then we have LDI R20 0 cross 0 9, um, it is in begin, it has used this, but we are using 0 cross 0 9, and then we are outputting TCRO 0, this R20, and again um, we have uh, uh, we have read TFR, and if 0 C F0 flag is set, skip next instruction, you will be skipping next instruction, and in out TCCR 0 R20 stop timer 0, this line can be omitted, but we are just using it to elaborate it. So in the last, that is out TFR 0 R20 clear OCF0 flag, and R17 and R16 we are toggling D3 to D17, and in port BR17 we are toggling BB3. So if we move on to the next one. So the next one says that using a prescaler of 64, write a program to generate a delay of 1920 microsecond. Assume XTAL is equal to 8 megahertz. So timer clock is 8 megahertz divided by 64 is equal to 105 kilohertz. Time period 1 by 125 kilohertz equal to 8 microsecond, and timer value is 1920 microsecond divided by 8 microseconds equal to 40. So over here we have delay of R20. I think this is the same program that is copied again. So there was some problem in Atlas Studio that our programs were not being updated. So over here, if I discuss example 9.5, example 3, 9.3, calculate the frequency of square wave generated on pin port P. 5, assume that XTL is 16 megahertz. So we are using a expression of 16 megahertz, and we have to calculate the frequency of square wave generated on pin of port B, fifth pin. So yeah, to get the more accurate timing, we need to go add clock cycles due to in the instructions. So we are adding clock cycles for each command. So this will be called 3 times. So we are in 3, then we are 1. One is this one. The delay has 3 cycles, and the one is this again has 2. This simple EOR node has 1. Then all are 1. Then just this SBIS is 1.5, and this reset is 4. So it's actually 25. So again, time we will use t is equal to 2 into 14 plus 25 into 0 0.0625 microseconds, that is 4.875 microseconds, and f is equal to 1 by t, so it will come to 05.128 kilohertz, and we have converted it in hex and decimal. So in 9th example, in the delay generated by the timer O in the following code, using both of the methods of figure 9.8, do not include the overhead due to instruction. So the crystal is again 16 megahertz. So over here we are using in the stack that is add its definition from example 93, and that is stack we're using, and then SVIDRB using port 5, that is fifth. So PB5 as an output, so it is using as an output. So EOR R17 R16 gives toggle of D5 of R16, then output B R17 gives toggle PB5, and then this is TCNT 0 R20, that is load timer 0, TCCROA R20 normal mode, and this in normal mode internal clocker no prescaler or using TCCROB R20. So TIFR 0 TOVO, if TOVO is set, skip next instruction. So next we have TCCR OB R20 stop timer 0 R20 uses R20 is to 0 cross 0 1. 0 gives us R20 is clear TOVO flag. Next we have 97, assuming exterior crystal at 16 megahertz, that the program will generate a square wave with a pre uh, period of 6.25 microseconds on pin port 3. So for square wave with t is equal to 6.25 microseconds, we must have time delay of 3.125 microseconds because XTL 16 megahertz. Um, the counter counts up vary every 0.0625 microseconds. This means that we need 0.3.125 microseconds, divided by 0.0625 microseconds is equal to 50 clocks. That is 256 minus 50 is equal to 206. So 0 cross CE, that is 0 is 206. Therefore, we have TC and T0 is equal to 0 cross CE. So first we are using adding is definition, for example 93 in stack. Then we have PB3 output toggle PD3 of R17 toggle PB3 timers delay, and we are using, and then we have out as DC and TOR20 load timer 0. Then we have out as normal mode. Then we have out is CROB R20 is normal mode in CL clock and no prescaler. SBIS is the command if TOVO is set, skip next instruction, and DCCROB R20 is for stopping timer 0, and DAFRO R20 is clear TOVO flag. Next, we have modified TC and T0 in example 7 to get largest time delay possible. Find the delay in milliseconds. In your calculation, exclude the word due to the instruction in the loop. To get the larger delay, we make TC and T0. This will come up from 00 to 0 cross 55 and FF, and then roll over to 0. So we are adding in a definition, that is adding a init stack, and PB3 as an output. We are choosing a PB3 as an output, and we are recalling toggle PD3 or B17 and R17 is toggle BB3. So relay timer delay, we are using load timer 0. So we are using over here the parser, that if TVO has skip next instruction, and TCCROB at the stop timer and clear TVO flag. Now we have next examples. So 912 means you have to examine the following program and find the time delay in second. Exclude the overhead due to the instruction in the resume XTL. So over here we have examined the following program
and find the time delay in seconds, exclude the overhead due to instruction in the loop, assume XTL 16 megahertz. So it's a similar program that's where we are using PB3 as an output, and in begin we have toggle D3 or D7, and then we have toggle PB3. So that's timer delay. Timer is TC and TC is load timer 0 and TC ROA is normal mode timer. RO is load timer, RA is normal mode. DCC ROB R20 timer or normal mode and CLK prescribes is prescribes 64 R jump again RDI R20 0 then we have PB12 we have okay over here I have uh, out of DCR or VR20. Solution is TCN or this is the TCN tier 0 plus 7 0 is equal to 16 in decimal form. Minus 16 is equal to 40 cross 64 cross 0 cross 0 6 to 5. Okay. Then we have 913 in the GMXT value equal to 60 megahertz. And the clock period fed for any timer 0 the first scalar option of 0 to 4 is chosen. Show that in the is the largest what is the largest time delay we can have getting using free scale option timer. So larger है 0.00 0.016384. So if I move on to the next program, assuming XGAL and 16 megahertz, where the program to generate a square wave of alpha hertz frequency of PB3. PB3 and the user timer on mode base scalar. So T is equal to 1 divided by 54 milliseconds, the period of square 1 by 2, and for the high and low portion of the pulse is 0. So we have the 0 1 by 250 has 0 performance. Okay, so look at the following steps. T is equal to 1 by 250 hertz and equal to 4 milliseconds, the period of the same wave, square wave 1 by 2 of its value, and log portion of 3. So it gives us 1 by 2 of it as a high and low portion of the pulse to millisecond to millisecond divided by 0.0625 microsecond divided by 256. So if it is in decimal and in hexa, it is 0 cos 83. So TC and T0 is equal to 83 in hex. So we will be using it, and so here we have 16 program. So it is same as first one where we have did. So it is exactly like that. Let me read the statement. Find the frequency square generated in the following code, and the duty cycle of the wave assuming is TS. So it is same. It is done previously. So um, in the following program, we are counting a square wave of 50% duty cycle with equal portion high and low on the port 3. Wait the timer 0 is used to generate the time delay, analyze the portion. So find the delay generated by timer 0 is the following program do not include the overhead due to instruction XTEL equals 16 megahertz. So we are using loading data as R16 and one is less than 3 if we say output. So 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 all these timer forms are just similar as we are using a different crystals and somewhere crystal different values and all our others are same in the same way that we have done previously. So randomly pick some program and study that. So we have SCR1, SCR1, DCR1, A, DCR1B, or OCR1BH, OCR1BL. So similarly, these things are happening quite good. So thank you very much for this video.